Hey YouTube, what's up? Dr. T here in St. Petersburg, Florida. And from the new series I'm bringing, Specials, here we will have part 2 of 3 about the NASA James Webb telescope.
Of course, by now they're much farther away than they were when we saw them. So those things are not there anymore. They have gone on to do something else. Some parts of the universe we'll never see because they're accelerating away from us now. So they're going to accelerate away so far that the light from them will never get here.
As we look deeper and deeper and deeper, we see fewer and fewer galaxies. It is not that we're running out of galaxies. It was the fact that as the universe is expanding and stretching across space and time, its light is being redshifted, and the galaxies from the very early universe are being shifted out of the view of the Hubble Space Telescope.
The Hubble telescope can only see what you can see with your eye, the wavelengths that your eye is sensitive to, plus a little bit of ultraviolet and a little bit of infrared.
Those galaxies are so far away from us that as light travels through space and space is expanding because the universe is expanding, the light gets redshifted. So it changes from blue light into red light as it travels through space.
It's so far away from us and so far back in time, its light only reaches us via infrared wavelengths.
The Webb is going to give us infrared eyes, and we'll see a part of the universe we've never seen before.
The Hubble Space Telescope has transformed our knowledge of the universe. But we haven't been able to study the first galaxies that formed in the universe. We haven't been able to find their light. And that's what the James Webb Space Telescope would provide. We can fill in one of the biggest missing pieces. When did the first stars and galaxies turn on? We'll detect the first light that formed from the first stars and galaxies in the universe.
We have enough sensitivity with our telescope and our instruments to detect a child's nightlight located on the moon. You could see things, on the order of a candle, a match, a lit cigarette. I know that if you were to certainly take your radiant heat, which for a human is about 80 to 100 watts, and stick it on the moon, we would easily be able to detect that.
It can even pick up the heat of a bumblebee. That is completely astonishing to me, even knowing that that's our telescope and we built it that way.
Yes, I've heard that. In fact, I was asked about it. I'd have to sit down and do the math very, very carefully. I've learned one does not argue with Nobel Prize winners unless you're 300% certain that you're correct. Although I'm quite certain you can see the nightlight.
I heard about this calculation. I checked it myself. I believe it's correct. Yeah.
If we had the moon here and the Earth 250,000 miles, what we need to do first is calculate the area of the sphere. 4 pi times 10 to the 1 joule per radius, which is 400,000 kilometers. Frequency times 12.5 per second squared. Gives us 4.2 plus half 2.2 energy by average frequency times 10 like constant 12.5 times 2 times 10 on something like 1.5 approximately. 1.5 milliwatts. If our insect were radiating that much, and I'm not an entomologist, don't know exactly how much an insect radiates, but that doesn't seem out of the realm of possibility.
A bumblebee gives off how much energy?
Well, let's see, it gives off about 50 milliwatts of power.
It does seem reasonable, but we could see a bumblebee on on the moon with our telescope.
And 50 milliwatts of power at 250,000 miles
Yeah.
is measurable.
Yeah, it's measurable.
That's a bumblebee as opposed to a yellow jacket as opposed to a hornet, but we could collect the light. Should know better than to argue with our chief scientist.
You have to take a time exposure to get something that sensitive. The bumblebee shouldn't move.
The bumblebee has to hold still.
Yeah, and bumblebee has to hold still. But of course, the most distant universe looks like it's standing still.
Brian, are you ready? Ready. Going up.
We don't want the telescope portion, the Webb telescope, to see any of the sun. The light that we're looking at are in the infrared. So in order to detect heat signature, infrared signature, it obviously needs to be very cold, or all it's going to measure is just itself, basically. So we need to keep it very cold. And in space, really the only thing that'll heat you up is the electronics that you've got and the really bright source, which is the sun. The telescope is generally kept around 30 Kelvin, so that's very, very, very cold. You know, I have no idea what it is in Fahrenheit. Yeah, I don't really work in Fahrenheit very well. 30 Kelvin, wow, how do we, 30 Kelvin Fahrenheit. Okay, 30 Kelvin is minus 405 Fahrenheit, so let's just say coldest ever on Earth. Okay, the lowest temperature on Earth ever recorded is minus 135 degrees Fahrenheit. So this is just about three times colder than that.
Layer 1's running about 212 degrees Fahrenheit, and layer 5 on the cold side is running about minus 400 degrees Fahrenheit. So it's approximately 600 degrees or so between the two, between the layer 1 and the layer 5.
So this sun shield is a really, 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 really good SPF. It's about 1 million.
There's nothing I can say that can come close to describing how technically difficult this telescope is. We are at the verge of impossible.
This is an engineering marvel. It's not actually necessarily just a scientific marvel, because we built big telescopes before. I built an 8-meter telescope on the ground. We used 300 tons of steel to build this telescope. Well, there's no way to launch a telescope of that scale into space. The James Webb weighs 6 metric tons. We have to go from 300 tons down to 6 tons. There's no rocket big enough to launch anything this big, so we then have to work out how to fold this telescope up. We had to create this origami telescope. Even the launch has to be perfect. As we launch this thing, the air must actually come out of all those sun shields in precisely the right way. The actual spacecraft must rotate at just the right rate so we don't fry the delicate structures and electronics, because the sun is powering down at one side. And as it leaves the atmosphere, it must be in exactly the right trajectory to actually hit the orbit in the right place beyond the moon. If it doesn't, we'll run out of fuel and this spacecraft will only have 4 or 5 years left. There are over 300 or 400 different operations that have to occur to make this telescope actually come to life. And a huge sunshade has to deploy, which is the size of a tennis court. At this point, things get pretty critical, because now everything starts to cool quickly. So now we've got to get the telescope unfolded before it gets too cold and the joints freeze up. Then we've got to get the mirrors unfolded. We've then got to get the instruments started. And each one of these things has to work perfectly first time. We get one shot to get this telescope right. The slightest thing goes wrong, then this mission can fail.
We lived in Florida, and I could see the Apollo launches from our backyard. We could see them as they cleared the horizon and up into the clouds, then would run inside to look at the black and white television to see the NASA simulation of what was happening. And for me, that was it. That's when I knew that I wanted to be involved in the space industry. We were exploring another world. In the 1960s, another world was the moon. So now this is the opportunity to go and look for planets around other stars. James Webb is going to enable us to look at exoplanets, to observe planets around other stars, to really understand their characteristics. We don't know yet what we're going to discover, but we have the instrument that's going to help us really understand those planets.
Another Earth is undoubtedly out there. In our own Milky Way galaxy, we have hundreds of billions of stars. Our own universe has hundreds of billions of galaxies. To me, personally, it is definitely there. We believe that every star in our Milky Way galaxy should have at least one planet. And we're hoping to find and identify a pool of transiting planets in the habitable zones of small stars. We call it the Goldilocks zone. Not too hot, not too cold, but just right for life. We're betting on the fact that nature delivers, that nature has created many rocky planets, and that life can originate and evolve anywhere given the chance. And we're planning on finding it. The James Webb is going to revolutionize exoplanet atmosphere studies. We'd like to find water vapor, because water vapor in a small planet indicates a liquid water ocean. All life on Earth needs liquid water, and it's a great place to start to identify a habitable world. We'd like to see carbon dioxide. It indicates that it's truly a rocky world. But beyond water vapor and carbon dioxide, what we'd really like to find are gases that don't belong. Here on our own Earth, we have oxygen. But without plants and other photosynthetic life, we would have virtually no oxygen in our atmosphere. If we're really lucky, and that would be literally like winning the lottery 5 times in a row. If there are planets around every small star, and there are many, many of those in the habitable zone, and if all of those have life on them, and if that life, half of it, let's say, produces gases, we actually have a shot of detecting that with the James Webb Space Telescope. We have the shot at finding life for the first time in human history with the James Webb Space Telescope.